Okay, we are now recording. So, oh, I look cool. Okay, well, hey, that's what counts, right? Nothing else matters. Okay, so before we get into the nitty gritty, does anybody have any questions about anything? Um, yeah,
Yes.
okay, go
Um,
ahead.
Getting in through Canvas, but it said the ID was wrong, so I had to get in through the email you sent out.
Yeah, I apologize for that. I apparently typed it in wrong into Canvas. You want to count that? Okay, we'll count that as a wig point. Okay, 1 wig point for today. All right.
I have a question, Mr. Hendricks.
Okay, go ahead.
So during the quiz, I had to do some research, but I couldn't find a true answer. Do a proton and an electron have the same number of charge in coulombs?
Okay, that is something that I did intend to talk about during the class. The answer is yes. And I have some slides in here that are going to address that, but the answer is yes. The charge is exactly the same. It's just positive for the electron, negative for the neutron. Okay, well, let's go ahead and get started then. So now we didn't have a regular homework assignment today. We just had the quiz. So the question number 1 on the quiz, all of the things that I listed there, those are all instances where electron guns are still used. So electron guns are very important things to know about. And later on in the chapter, or later on in the book, in different chapters, we're going to be talking about some very important experiments that you need to know how electron guns work in order to understand what we're going to do there. So Jaron, you are correct. I have not yet graded it. Okay. All right, question number 2. So what we did in class that appeared to break the laws of physics was we calculated the speed for an electron that was faster than the speed of light. We put our numbers into the calculator correctly. What we didn't take into account was relativity, which we will learn how to do it, but not this week. That'll be later. Okay. And so here's the answer to that question. Relativity was what we didn't take into account. Okay, the secret phrase was bada bing, or no, it was not bada bing. The secret phrase was not sure. Okay, and now this one, I want to hear what you guys came up with for answers here. So we've got a 12-volt battery. Okay, I want to know how fast the electrons are going to be moving. So tell you what, I'll give you a little help here. So what you see here, these are the equations. Now this equation up at the top here, very, very important. Everybody needs to memorize that equation. You know me in memorization. I don't like memorization as a general rule, but there are some things that you must memorize. This is really important. If you memorize this one, it's going to help you a lot. So we rearrange that, so put charge up on top, and then we recognize that however much work we do on the electron, that's how much kinetic energy the electron is going to have. So that means the kinetic energy, 1/2 mv squared, is V times Q. So then we just solve for V. Now be careful, there's 2 V's in the equation here. Lowercase v is the velocity, uppercase V is the voltage. Do not get those mixed up. All right, so when we solve for this, we need to know what numbers to put into it. So Q is the charge of the electron, which you can look that up in the back of your book. And after doing a bunch of homework problems, it's a number that you're probably going to memorize. But if you ever forget it, it's always in the back of your book here. Okay. And then M, the mass of the electron, that's also in the back of the book. Okay. So when you do the math, put it in your calculator. Hopefully you got 2.1 million meters per second, which is really fast, but you know, that's what it is. Okay, and then the second one now, we got the proton gun instead of an electron gun. All right, and this time, instead of telling you the speed and asking you for the voltage, I did it the other way around. Instead of telling you the voltage and asking you for the speed, I did it the other way around. Okay, so we start off exactly the same equation. So down to the fourth line here is exactly the same, but this time, okay, since I swapped things around, this time what we want to solve for is delta voltage. All right, so we get this equation here, and when we put the numbers in, the answer, oh, by the way, now, and here we get to Josh's question. So when we put the numbers in, we needed to know what the mass of the proton is. So when I look in the back of the book, I see a thing that tells me the mass of the proton, so life is good. But I don't see anything that tells me what the charge of a proton is. Doggone, what am I gonna do? Okay, well,
knowing the fact that an electron has the charge of 1.6 times 10 to the, let's see,
negative
it isn't
19.
saying what the charge of a it isn't specifically saying charge of electron or proton. It's saying elementary charge.
Okay,
The
so
1.602.
so what it says here is elementary charge, and so you need to know that the elementary charge is the charge of an electron, which is also the charge of a proton. It's just negative for the electron, positive for the proton. So you need to know that, or you could Google it too. That always works. Okay, so Ellie is saying that that it was late because the due date was AM, not PM. Really? Oh boy, that's 2 WIG points. Oh, this is not good. It looks like I'm going to be wearing the wig before this day is over. Hang on just a sec. I need to cough. It's not because I have coronavirus. I just got something in my throat. Hang on. Okay. All right. Okay, so thank you for pointing that out, Ellie, and I will make sure that I don't mark it as, I will accept it as not being late. And I'll try to be more careful with my AMs and PMs next time. All right, so I've got 2 WIG points and we're only 10 minutes into the class. This is not going to be a good day. Okay. All right, and so anyway, when you put in all the numbers, I got 3,800 volts. Hopefully you guys did too. All righty. Oops, sorry. Okay, so we have done everything in chapter 21 that I think is important. So the next 2 chapters, chapters 22 and 23, they deal with dynamic electricity. Remember, chapter 21 was static electricity. That means electricity that's not moving. So 22 and 23, that's now we're into dynamic electricity. So the electricity is moving. And this is important stuff. It's something that I think everybody needs to know. But there's just too many cool things in the book and not enough time in the year to do everything. So I am going to skip chapters 22 and 23. At the end of the year, if we have time, I think I would like to come back and pick up a few things, but if you are interested in this, and I would hope that you are because it's really good stuff, I teach an entire semester-long class on electronics. A few of you have taken that class. Ouch, why do you say ouch? So anyway, a few of you have taken that class. If you're interested in electricity, take my electronics class next year. It's just a half-year class, and we go into all of the stuff from chapters 22 and chapter 23, plus a whole bunch of additional stuff, okay? And also another option you have is you can take my engineering class. In my engineering class, we also talk about these types of things as well. In the engineering class, it's only a small part of the class, so we maybe spend about a month on this and then we move on to other stuff. Whereas in the electronics class, we spend the whole semester on this. But for right now, we're going to go ahead and skip it because it turns out that you don't need to know this stuff in order to get on to the rest of the stuff which I think is really important. So chapter 24 is what we're going to start into now. Chapter 24 is magnetic fields. So remember, we had electric fields and now there's this other thing called magnetic fields, and they are very, very similar. They're not the same, but they are definitely related. Okay, so if you take a magnet, if you were to map out the space around that magnet, and when I say map it out, what I mean is take a small magnet and put that small magnet in there and see what direction it points, you will find out that the space around the magnetic field is going to look something like this. And some of you might say, hey, wait a minute, that looks really familiar. And yes, it is going to look very, very similar, almost identical to what you have if you have two charges, two electric charges right next to each other. So in fact, we have a name for it. When you have two electric charges right next to each other, we call that a dipole. So an electric dipole and a magnet, the field around them looks identical. But it's really important that you don't make a common mistake. So what I want to do is I want to ask a question here. And in fact, I'm going to use a new feature of Zoom that I haven't tried yet. Let's see how this works. So I'm going to ask the question, and don't type it into the chat box here. We're going to take a poll. All right. So you hopefully, no, why are you not seeing it? You should be seeing it on your screen right now. Okay, I haven't ever used this feature before. So my computer, my teacher computer, is telling me that you should now be seeing questions on your screen, but my student computer, where I see what you guys are showing, or what you guys are seeing, I'm not seeing it there. Rats. Are you guys seeing any poll questions appearing on your screen? No? Yeah, neither am I. Okay, I guess we'll just have to do it the old-fashioned way. I'll have to find out why the polling feature isn't working. Okay, so all right, so just go ahead and type your comments into the chat box. So, will an electrically charged object that's placed near a magnet, will it be attracted or will it be repelled? Okay, and I see some of you are thinking that it's a trick question. Some of you are thinking that it will neither be attracted or repelled. Me, would I ask a trick question? Yeah, I would. Okay, so Josh is saying, doesn't it depend on the charge? Okay. Some people are saying repelled, except then they've realized, yeah, it is in fact a trick question. Yes, but it's an incredibly common misconception. Lots and lots of people think that, in fact, let me go back up here again to, okay, because a magnetic field looks so much like an electric dipole, a lot of people get them mixed up and they think that magnetism is basically just static electricity. And so they think that if you take a positively charged object here, it would be repelled. But in fact, that's not the way it works. The way that it works is that electric charge, if it's not moving, it couldn't care less whether there's a magnetic field there or not. It will not feel anything, either attracted or repelled. But the key here, and I put it in bold here, the key is the charge has to not be moving. Now this is where physics gets really interesting, one of the many places where physics is really, really interesting. If the charge is moving, then things change. A moving charge will feel a force. A static charge will not, but a moving charge in a magnetic field will feel a force. Okay, but even then, it won't feel a repulsive or an attractive force. It will feel a force that's pushing it off at 90 degrees. Okay, so the force it feels will be perpendicular. So in this case that you see right here, okay, so if the object is moving in the direction that I have shown in the screen here, the direction of the force that it's going to feel will be out of the page. So it's not toward the magnet or away from the magnet. It's 90 degrees. It would feel a force coming out of the page. And if it was moving the opposite direction, it would feel a force that's pushing into the page, which is really weird, okay? But that's physics, that's the way it is. Now in your homework tonight, we're not going to be dealing with moving charges in magnetic fields, but we will on Wednesday. We will come back to this on Wednesday. But for right now, all that I need you to know is that a charge that is not moving will not feel any force at all from a magnetic field. Won't be attracted, repelled, and it also won't be pushed off at that funny angle. Okay. All right. So do not make the mistake of calling the plus this end of the magnet here. Do not call it the plus end. Okay, I see students do that all the time. They draw a magnet, and the side that has the field lines coming out of it, they call it the plus end of the magnet, and the other one they call it the minus end of the magnet. Do not do that. Okay, even though it looks that way. I mean, if you look at the magnetic field here, it does in fact look like that's the case. But do not call it plus or minus. Make sure you call it north and south. Okay, so Milo is asking, what's the chances of a charge not moving? Well, as far as we're concerned, for any homework problems, it's really good. But I mean, if you look at the atomic level, okay, that's going to be different. In fact, we're going to talk about the atomic level in just a couple of minutes here. Okay, so yeah, I figured that's probably what you meant. Yeah. Okay, so a magnet does not affect a charged particle if it's not moving, but a magnet can certainly affect another magnet. Okay, so you can see this is a picture that I took out of the book. So they've taken a bar magnet and they've hooked it up with the string hanging from the ceiling so that it's free to spin. So if they take another magnet, okay, and they put it right here, so we got north against north. So remember how like charges, electric charges, like charges repel? Okay, well the same thing is going to be true with magnets. If you got the north end of a magnet here and the north end of another magnet here, they are going to repel each other. And so what's going to happen is that magnet that you see there is going to spin around so that the north end points away from the magnet he's holding and the south end points towards it. And you guys have all played with magnets, right? Okay. Now, you have presumably all used compasses at some point, and that what I just described up here is exactly how a compass works. So with a compass, you've got a tiny magnet, and it's sitting on a pin or something where it's free to rotate. Okay, so when you hold that magnet anywhere near the Earth, that magnet is going to orient itself like this, so that the north pole of the magnet, or at least the end of the magnet that points towards the north, we're going to call that the north pole of the magnet. Okay, so obviously inside the Earth there is a huge buried magnet, or at least something that serves the same role. And it's interesting to note that the magnet that's buried inside the Earth is actually oriented this way. The magnetic south of the Earth's interior magnet is the one that's actually aligned with the Earth's magnetic north pole, because otherwise it wouldn't work out to where the magnet that we hold here points to the north. So yeah, inside the Earth, there is effectively a great big magnet buried. And we're going to come back in a couple minutes. We're going to come back and we're going to talk about what's actually happening inside the Earth. But for right now, just this is a good way to think about it. So no matter where you are on the Earth, it'll point to the Earth's magnetic North Pole. Now, those of you who've done any kind of orienteering, any type of, maybe in Scouts, or if any of you have been lucky enough to ever go sailing, you hopefully know that the Earth's magnetic pole is not exactly lined up with the Earth's geometric, or geographic actually is a better word. The magnetic North Pole and the geographic North Pole are not exactly the same. It's off a little bit. So if you get up too far north here and you're relying on your compass, you can get yourself into some big trouble. But as long as you're reasonably south, it'll work really well. And when we talk in a few minutes, when we talk more about what causes magnetism, we'll come back to this. But just be aware that the magnet doesn't exactly point north. It's a little bit off. It's some spot somewhere in northern Canada right now is where the Earth's magnetic North Pole is right now. And that changes over time. Every year that goes by, the magnetic North Pole moves just a little bit there. Okay, So what is it that causes magnetism? All right, well, what you're seeing right now is a diagram which, if we were in class, I wouldn't just show you this diagram. I would actually do this for you. I have all the equipment in my classroom necessary to do this experiment. I have a compass and I have a power supply, which is, think of it as basically just a battery, but it's a neat kind of battery because you can adjust the voltage on it. Okay, so notice right here, can you all, okay, so on the left here, the power supply is in the off position, so electricity is not flowing through this wire. So if you hold the compass, it holds the compass will point to the north like compasses do. But when you turn the current on, so electricity is now flowing through the wire, that compass needle rotates, okay, depending on what direction the current is going, okay. And if the current is strong enough, that compass needle will rotate a full 90 degrees. And if I switch the current, so the current, if I were to take this plug here that's into the plus right now, if I were to swap the plus and the minus so the current is running the other direction, what you'll see is the needle will flip 180 degrees and it'll turn the other way. And this is something that, according to legend, was discovered totally by accident. Oersted was doing a bunch of other experiments on other things, and according to legend, he just happened to have a compass sitting there, and he looked at it and says, hey, wait a minute, this compass is pointing the wrong direction. What's going on? Now, you do have to be careful with these legends, because remember, the legend also says that Isaac Newton discovered gravity when an apple fell on his head, which most historians think is bogus. And also people say that Galileo dropped the two rocks from the Leaning Tower of Pisa, which most historians say is bogus. But so you got to be a little careful with that. But anyway, this is definitely true. And if we were in my classroom, I would show this to you and let you play with it. And this experiment, this changed physics forever. This was earth-shattering. This was on the level of, you know, Thomas Young's double slit experiment, how important that experiment was. This is the same level of importance. This really revolutionized physics. This showed that electricity and magnetism are connected. Up until Hans Oersted did this, everybody assumed that electricity was a totally different beast than magnetism. Yeah, they had some similarities, you know, kind of like electricity and gravity has some similarities, right? But everybody assumed that that electricity and magnetism were separate things. But when Hans Oersted discovered this, people realized that the electricity and magnetism are actually very closely connected, okay? And in fact, Oersted's experiment explains why it is that a moving charge is affected by a magnet, because a moving charge is a magnet. Now, that's not really the best way to say it. The best way to say it is a moving charge creates a magnetic field, but I mean, what's the difference, right? Okay, so a moving charge creates a magnetic field, so it becomes a magnet, okay? So here is a good way to think about it. And again, these are pictures that I took right straight out of your book. Okay, so let's suppose that we have the current is flowing through this wire, and the way that this picture is drawn, the current is flowing from top to bottom. Okay, so if you were to take a bunch of little magnets and you were to place them around the wire, what you'll find is that they go in the pattern shown here. Right here, you see the arrow is pointing this direction. That means that if you place a compass here, the north arrow of the compass will point in that direction. Whereas if you put it here, it points this direction, here it points this direction, here it points this direction. So the compass will always point tangent to the circle that's drawn around the current. So if the current is flowing from top to bottom, the compasses look like this. But if you swap the direction of the current, so the current is flowing from bottom to top, those compasses are going to flip. Okay, so So what you get can be shown over here. And so scientists have given it, this particular rule, a name. We call it the right-hand rule. And so imagine that this pen is a current, a wire that's carrying current, and imagine that the pointy end of the pen is the direction that the current is flowing. And by the way, we should probably talk about this. All of this stuff, all of these rules that we're talking about right now, they were all developed before anybody knew that there was such a thing as an electron. So let me go back up here. Okay, so when people hook up wires to batteries, okay, there's a plus side of the battery, there's a minus side of the battery. So people knew that something was flowing through the wire, even though they couldn't see it. They didn't know what direction it was flowing, and they didn't know what it was that was flowing, but they knew that something was flowing. Okay, and like I said a second ago, people had not yet discovered that there was anything like an electron and a proton. They didn't know anything about those. Okay, so what they did, and Ben Franklin is the one that gets the credit for doing this, is they just kind of flipped the coin and they said, okay, so we're going to assume that whatever it is that's flowing is flowing from the plus side of the battery to the minus side of the battery. Now they had a 50-50 chance of being right. And what do you guys suppose? Now that we know what it is that's flowing, did they guess right, or did they? Yeah, okay, so Milo is saying they guessed wrong, and Milo is correct. It turns out they guessed wrong, but they didn't know that until they had already developed all these rules here. So this right-hand rule that we're going to be using here, this was developed before they knew about electrons. And so when you're doing the right-hand rule, or whenever you're doing anything with electricity, all of the assumptions are, all of the conventions are built on the assumption that the current is flowing from the positive to the negative, which we now know is wrong. But that's okay. We stick with it anyway. Okay, so here is a pen which represents a wire that's carrying current, and the pointy end of the pen tells me that's the direction that the current is flowing. So it's from the bottom to the top is the way that the current is flowing. Okay, so what we're going to do is we're going to take our right hand, and it has to be the right hand, and we're going to grab the wire, or in this case the pen, but the wire, we're going to grab it with our thumb pointing in the direction that the current is flowing, the positive current, okay? And then our fingers will wrap around there, and you can see that our fingers will show you what direction the magnetic field is going to be, all right? So if you look at the picture here, okay, you look at the person's fingers, so his thumb is pointing in the correct direction. So the way his fingers are curled, over here on the left side of the wire, if we were to hold his fingers differently, the current is coming out of the page towards us over on the left side of the wire. Directly in front of the wire, the current is going to our right. On the right side of the wire, the current is going into the page, and then behind the wire, the current is going to the left. Okay, so that's what it means when we curl our fingers like that. Okay, so this is something that you got to kind of think about and play with a bit. Let me just pause and make sure everybody's following along here. Is this making sense, everybody? Am I going too fast or too slow, or can you even hear me at all? I need to see a little feedback. Okay, so people can hear me. It's going great. Okay. All right, so whenever you have a wire, just grab it with your right hand so that your thumb is pointing in the direction that the positive charges would be flowing if positive charges were the things that are flowing, even though we now know they're not. Okay, and then the curl of your fingers, that will tell you. So you see over here, they're coming towards you. Right here, they're coming actually to your left. Right here, they're coming back towards me now. And then over here, they're coming to your right. Okay, so make sure you know the right-hand rule. Okay, so Bridget is asking, is the direction of the magnetic field the direction of the compass pointing for north? Yes, that is correct. That is what the magnetic field means. Okay, all right, so let's suppose you have a loop of wire. All right, so I've got a battery over here, and the wire is connected to the plus side of the battery, the minus side. So we're going to assume that the current is flowing from the plus side to the minus side. Okay, so it doesn't matter where you grab the loop. Let's see. Okay, so here's a wire. Okay, so it doesn't matter where you grab it. Okay, so if I grab it right here, so let's assume that the current is flowing this way. So over here, down here, it's flowing that way. Over here, it's flowing up. Over here, it's flowing that way. So if I were to grab it right here, I want my thumb to be up. So I grab it like this. So you can see that inside the loop here, the magnetic field is coming towards me, okay? Whereas outside of the loop, the magnetic field is going towards you. Okay, so in here, the magnetic field is pointing towards me. What if I grab it up the top here? Well, again, inside is going to be coming towards me. What if I grab it down on the bottom? Well, again, inside the field or inside the loop is coming towards me. So it doesn't matter where I grab it. Anywhere inside the loop, okay, the loop shown here, the magnetic field inside the loop is going to be coming out of the page, and the magnetic field over in this region is going to be going into the page. The magnetic field in front of the loop is going to be going that way. Magnetic field behind the loop is going to be going the other way. Okay, so on the picture here, the in front and in back, that gets a little confusing. This right here, this is the part in front. You can see, if you look closely, you can see the lines are passing in front of the loop. And back here, it's hard to tell, but if you look closely, you can see the lines are passing behind the loop. So in front of the loop, the fields are going this way, and then behind the loop, they're going the other way. Okay, so the first right-hand rule will tell you how this works. Now, using this, we can figure out what direction the magnetic field lines are going on this setup right here. This is a setup which I hope that you have not only seen before, but you've actually done before. If your junior high school science teacher earned his or her paycheck, you should have done this experiment in junior high school. You should have taken a battery, you should have taken a nail, wrapped a bunch of wires about it, and it becomes a magnet. So how many of you did this in junior high school? So Bridget, you got cheated. Oh, Ellie, you got cheated. Zach got cheated. Anna got cheated. Holy cow. Okay, Dean didn't get cheated. Jaron isn't sure if he got cheated. Hiram just watched Bill Nye. Okay, hey, you can never go wrong watching Bill Nye. Okay, so anyway, if you haven't done it, hey, this is a good thing that you guys can do at home. You've all got batteries at home, right? You've all got nails at home, and hopefully you got wire. Some of you may not have wire, but I want everybody to do that, okay? In fact, let's make it a homework assignment, an unofficial homework assignment. I won't give you points for it, but I want everybody to get a nail, wrap it with wire, hook it up to a battery, and verify that it does in fact become a magnet, okay? A lab, yay, Josh is glad to see a lab. Okay, all right, now, here's the question for you. So you guys all trust that it will become a magnet, right? Here's the question for you. Which end will be the north side of the magnet and which end will be the south side of the magnet? Using the right-hand rule that we just talked about, it's possible to figure out. So I'm going to pause for a bit here. I'm going to let you guys chew on this for a while. So Anna was saying, how can you tell if it becomes a magnet? Well, take a bunch of paper clips and hold the paper clip underneath it. And if the paper clip is attracted to it, then you know it's a magnet. Okay, so I want you guys to think about it. Can anybody figure out how you could use the right-hand rule to determine which end of the nail is going to be the north end and the south end? Is the pointy end going to be the north side of the magnet, or is the other end going to be the north side of the magnet? I propose to you that you have enough information right now that you could figure that out. And the trick is use the right-hand rule. So I'm gonna pause while you guys think about it. How could you figure it out? Okay, so top. Okay, so Jaron is saying top is north, but you got a question mark on it. So Jaron, if you've got a question mark on it, then I'm going to say the answer is wrong because of the question mark. You should be able to tell me either yes or no without a question mark.
Here's my reasoning, because when I do the right hand method, due to the fact the positive is flowing from the bumpy part of the battery to the back side, the current ends up flowing upwards, you could say, so my thumb ends up sticking upwards.
Very good, Jaron. Your logic is perfect. That's exactly what I wanted you to do. So those of you who are brave enough to answer, which is only 2 of you, you are correct. Okay, so if you use the right hand rule, okay, so what you do is take your hand and grab the wire and anywhere, like, can you guys see? Okay, see where my arrow is pointing right now? Let's say that that's the spot where we grab the wire. Okay, so the current is coming in here. So if we grab it at this spot, the current is going from the left to the right. So if we grab the wire with our thumb pointing the correct direction, when our fingers are inside the coil here, our fingers are going to be pointing up. When our fingers are outside the coil, they're going to be pointing down. And so it doesn't matter where we grab it. We can grab it anywhere we want here. Anywhere inside the coil, our fingers are going to be going up. And that means that the north side of the battery is going to be up on top, or north side of the magnet, sorry. North side of the magnet is going to be up, and the south side is going to be on the bottom. So the right-hand rule is what's going to answer this for us. Now in your homework tonight, you're going to find that there's really not much, if any, calculation to be done. All of the questions in the homework tonight are going to be qualitative rather than quantitative. They're going to be questions like this. They're going to be which direction is the north end of the magnet in this particular case. Okay, so hopefully that's pretty straightforward. Now, the book, they tell you about something that they call the second right-hand rule, which I think is totally unnecessary. I think you don't need the second right-hand rule. I think the first right-hand rule, if you think about it the way that we just thought about it, then you're good. You don't need this second right-hand rule. But the book talks about it, so I better talk about it too. Okay, so what they're saying is that if you have the nail and the current is wrapped and the wire is wrapped around it the way that you see here. So when it comes in on top of the nail, and then it goes around behind the nail, and then it comes around on top. So anywhere where the wire is on the side that we can see, the current is always going upwards. And anywhere where the wire is on the back side of the nail, the current's always going downward. Okay, so what they are saying is, with the second right-hand rule, they're saying take your fingers and wrap your fingers around the nail, around the coil, so that your fingers are pointing the same way that the current is flowing. And they're saying that your thumb then will point to the right, to the north end. So if we go back up here again, if we use the book's second right-hand rule, what they're saying is we want to grab this so our fingers are going to pass on top of the coil in front, and then behind the coil they're going to be going like that. So if we grab it like that, then our thumb will be pointing towards the north end. So the second right-hand rule it's really the same as the first right-hand rule. So I don't know why the book has 2 right-hand rules, but they do. So okay, we can live with it. Okay, so don't be surprised when you see this. And if you read ahead and you want to get a preview of what we're going to do on Wednesday, you're going to find that there's actually a third right-hand rule, but I'm not going to talk about it right now. I'm going to save it for Wednesday, but just be aware there is a third one coming. Okay, so I think we've already talked about that. Let's move on. Okay, so now let's get back to the question of why is the Earth a magnet? Is there really a magnet buried inside the Earth, or is there something else happening that causes a magnetic field? So Yazan is saying, yes, there really is a big magnet buried inside the Earth. Well, effectively, I mean, there is something happening inside the Earth that's creating a magnetic field. So let's see what that is. Okay, so a few minutes ago, somebody, I think it was Milo, was asking about what's happening at the microscopic level. What is magnetism really? Okay, well, remember how we said that a moving charge creates a magnetic field? That's it. That is the answer. So if you look at the atomic level, what's happening is here is an electron, here is a proton. That electron is moving around the proton, and the fact that that electron is moving creates a magnetic field. Okay, and if you use the right-hand rule, you can figure out what direction the magnetic field is. Except now, some of you who like to catch me on wig points, some of you might look at this picture and say, "Hey, wait a minute. The field lines are moving or pointing the wrong direction." If we use the right-hand rule on this picture that we've got right here, the north end should be at the bottom, not the top. So before you go calling me a wig point, oh, and Ian, you are correct in that. So I'm going to come back to your comment there. But before we do that, why is this not a wig point? I mean, at first glance, it looks like this picture, the arrows are going the wrong direction. But I claim that it's not a wig point. Anybody got any ideas why it's not a wig point? I need to see something typed here. Yes, Jaron, you got it exactly right. Okay, because the electron is negative, not positive. So if you have a negatively charged particle moving to the left, that's the same thing as if you had a positively charged particle moving to the right. Okay, so there's two ways that you could approach it like this. One is whenever you have a negatively charged particle that's moving, you could just say, okay, well, negative to the left is the same thing as positive to the right. Or the other way to approach this is just say, if the charge that's moving is negative, then instead of using our right hand, we use our left hand. Okay, so then it becomes the left hand rule rather than the right hand rule. Okay, so anyway, so if you have a positively charged proton here and a negatively charged electron, and that negative charge is spinning around it like that, that creates a magnet. Okay, so any hydrogen atom is a magnet. What about a helium atom? Would a helium atom be a magnet? Because how many electrons does a helium atom have? It has 2 electrons. And you guys in your chemistry class, you've talked about the spin of electrons, right? Okay, so in a helium atom, you've got 2 electrons. One is spinning the one way, the other is spinning the other way, and so those 2 magnetic fields are going to cancel each other out. So a helium atom is not going to be an electron, it's not going to be a magnet. Okay, and if you've got what you see here, so this is some random other atom. So it's got a whole bunch of positive charges and negative charges, and it's a whole bunch of electrons. So maybe it's going to be a magnet, maybe it's not, depends. It depends on a lot of things. When those of you that are taking the U of U chemistry class, you have hopefully learned by now that the shape of the electron orbit is very complex. Okay, what we're showing here is that the electrons are going around in circles, which turns out not to be the case. I mean, sometimes it is. You've got s orbitals and p orbitals and d orbitals. You guys remember? How many of you are taking U of U chemistry? If you're taking U of U chemistry, can you just type in a yay or a hi or something like that? Okay, so Yasmin is Bridge. Okay, so some of you are taking U of U chemistry. So you've talked about s orbitals and p orbitals and d orbitals, right? Okay, so it gets really complex. So the bottom line at the high school level anyway, is that that some atoms, depending on how many electrons they have and depending on the shapes of the orbits, some atoms are naturally going to be magnetic, some atoms are not, okay? All right, now, even atoms that are magnetic, that doesn't mean that the entire substance is going to be magnetic. So iron is the best example because iron is the most commonly used one. Okay, so if you were to take a piece of iron and look at it under a microscope, what you're going to find is that the iron molecules are all randomly arranged, like you see up in the top part of the screen here. So this atom right here is a little magnet with its field pointing that way. But right next to it is another atom that's randomly aligned, so maybe it's pointing the other direction. So if you got a whole collection of randomly aligned molecules, the substance as a whole, they're all gonna all cancel out, and so it's not gonna be a magnet. Okay, so even if you look on the atomic level and you say, okay, this atom is a magnet, that doesn't mean that a clump of those atoms is going to be magnets, okay? Because they're probably going to be randomly oriented. So in order for it to act as a magnet, we need some way for all of the atoms to get aligned in the same direction, okay? So magnets, it used to be that you could find magnets lying around. You know, if you go walking around in a place where nobody's ever walked before and you see a bunch of rock here, some of the rocks that you pick up might in fact be natural magnets. In fact, we have a word for them. We call them lodestone. You're not going to find many of them anymore because there's been so many people walking around picking them up. But okay, so here's what happens. Here's how natural magnets form. Okay, so back in the old days when the Earth was very volcanically active, there was lava flowing out. In fact, even now in many places, it still does flow out. But especially back in the early days when the Earth was first forming, there was a lot of lava coming out. And you guys may know that the Earth's core has a very high percentage of iron in it. Okay, so when the lava comes out, if it's got a lot of magnet or a lot of iron in it, okay, it's fluid, so these iron molecules, they can all flip around whatever they want. And so if this lava comes out on the surface of the Earth, and if the Earth has a magnetic field, which it does, what's going to happen is each one of these little molecules, because they're in a liquid state right now, so they're free to rotate, so they are going to all align themselves with the Earth's magnetic field. And then as the lava cools, okay, they stay locked in place because the Earth magnetic field. So then the lava cools, so all of the atoms in there, they're all pointing the same direction. And so then later, after it cools, okay, so now you pick up a chunk of it and you look at all the atoms and you see all the atoms in there, they're all aligned the same way. So what you have is a natural magnet, which is called lodestone. Okay. And in fact, even now, if you want to take a piece of iron that's not a magnet, okay, like for instance, if you want to take a nail, which is not a magnet, okay, if you want to make it be a magnet, what you can do is just heat it up, and then so it gets really soft. It doesn't have to go all the way to liquid. You can just heat enough to where it's really soft, and then put it in a really strong magnetic field. Leave that magnetic field on while it cools down, so that as it cools down, they freeze in place, all pointing the same direction. Okay, and then when it cools down and becomes solid, you've turned that nail into becoming a permanent magnet. Okay, and then the last little thing we need to talk about here is, why is the Earth a magnet? We haven't yet really talked about that, although Ian kind of hinted at it. Okay, so inside the Earth, we have a whole bunch of molten iron. The Earth is spinning. Inside the Earth, that molten iron is going to have to be spinning too, because if the outer crust is spinning, it's going to pull the inner along with it. But it's probably not going to be turning at the same speed that the outer crust is. Okay, so in effect, it's as if if you picture the Earth as being not spinning, you know, me and my friends at the Flat Earth Society, right? One of the things we like to think is that the Earth is not really spinning, but it is, of course. And if the core inside it is turning at a different rate, it's as if we're sitting still and the core is spinning. So inside the Earth, you have a bunch of molten iron, and it's so hot that it's been ionized. And so ionized means that some of the electrons have been stripped away. And so you've got positively charged liquid, which is flowing in a circle. And because the Earth is spinning on the north-south pole, it's not surprising that the magnetic pole is going to be pretty well aligned with the geographic North Pole, okay? Because you got these positive charges that are spinning in here like this, okay? Now, it's not going to be perfect because they don't necessarily have to spin exactly in line with the Earth's geographic pole, but it's going to be very, very close. And in fact, it is very close. Okay, so that's the reason why the Earth is a magnet. Well, that's pretty much it for today. Like I said, your homework tonight, you're not really going to have to calculate anything. It's going to be all qualitative, you know. Don't forget to take the daily quiz. I'll post that as soon as I get the recorded version back from the Zoom people. It takes them about an hour to process it. So as soon as I get that, I'll post the daily quiz. The daily quiz questions will be really simple ones. Yes, secret wordings, hidden word. Okay, yeah, we should do that. Okay, so let's see. Joshua, you were the first one to suggest. Oh, no, you weren't. Somebody suggested it before you did. Let's see, who was it that suggested that? It's already scrolled up here off my screen here. Okay, so anyway, okay. So Milo, looks like you were the one that suggested it first, I'm thinking. So Milo, what would you like it to be? Oscillation over thruster. Holy cow, Milo, why am I not surprised? Okay, well.
Have you ever seen Buckaroo Banzai from the 80s?
I remember seeing it long time ago. I've forgotten anything that I saw about it. Is that a big?
Oscillation over thruster is the device that allows the car, the supercar in the movie, to like move through solid matter.
Oh, well, that's cool. I'm going to have to go back and watch that again. It's been decades since I saw that. Okay, so that's the secret phrase for today. Oscillation over thruster. Why does that look backwards? That's funny. Does that look backwards to you guys too? Oh, hey, this is really interesting. I've got two computers here. On my teacher computer, it's backwards, but when I look at it on the student computer, I see it actually is correct. Well, that's funny. Okay, so anyway, that's the secret phrase for today. And then the rest of the questions on the quiz will be similar, easy questions. But that's not your only homework. Okay, here's your main homework. So chapter 24, problems 1 through 10, and also problem number 13, I think is a really important one. So I definitely want you to do problem number 13 also. You shouldn't need a calculator tonight. It's all just, you know, what direction is the field, you know, just basic problems like that. So, are there any questions on anything that we've covered today? So, nope, we good. Nope, okay. All right. So, I should do the dynamic electric on the test. Yeah, I probably should, but I ain't gonna. So yeah, don't worry, Bridget, I won't. No, not on this test. Okay, well, looks like we're all done then, so I'm gonna go ahead and stop the recording.